Welcome everyone. In this video we are going to derive the formula that describes the charging process of a capacitor in a RC circuit. Now, an important question to ask here is, what is an RC circuit? RC circuit, what is it? Well, it basically means that in the circuit there is a resistor and a capacitor. And there's also going to be a battery, a voltage source. So let me draw the circuit. And let me erase this. We don't need it anymore. Here is the battery. We have the resistor. And we have the capacitor. And you can realize that they are in series. Okay, the capacitor and the resistor are in series. This is going to be epsilon. This is the voltage across the battery. This is going to have a resistance value of R, and the capacitor is going to have a capacitance of C. Now, the question is, what is the charge as a function of time on this capacitor? What is Q of t? We want to find this. Of course, in terms of the given variables, in terms of R, epsilon, C, and of course t. And also, another variable, I will say that the capacitor is charged with Q naught initially, Q naught. And this is the positive side, this is the negative side, okay? Now the current is going to flow from the positive terminal of the battery to the negative terminal. And I'm talking about the conventional current, which is in the opposite direction of the flow of electrons. We have the conventional current, which I will denote with little I. With small case r, you can also denote it with capital I, but I prefer the small case I, especially since it is a changing current. When it is a constant current that I'm talking about, I prefer the capital case, okay? And okay, so you can see that why the capacitor will be charged further, because positive charges are going to build up on this plate, okay? And also negative charges will build up on that plate, obviously, as a result of the build of charge here. Or you can think of it, if you're thinking of flow of positive charges are leaving here, so it is becoming more negative. Okay, that is another interpretation. All right, so how do we start? Well, I want to say that this point is A, and this point is B. This is the label. Those are the labels of the points. And if I start at point A, I will have a potential, electric potential VA. Then I'm going to travel I'm going in this direction, by the way, in this direction. I am going around this loop, to be more specific. So I am going in the clockwise direction, okay? So we travel from the negative terminal of the battery to the positive side. That is going to be then a plus epsilon. The electric potential increased. Then we are traveling through a resistor. We are traveling through a resistor, and we are going in the direction of the current. And if we go in the direction of the current through a resistor, then the electric potential decreases, and it decreases by Ohm's law, which says it is going to decrease by I times R. And then for the capacitor, there is going to be another decrease, because we are going from the positive plate of the capacitor to the negative plate. And if we go from positive to negative, there is a potential drop. And how much it drops is, well, Q is equal to CV. And you don't need to take this for granted. I have a video where I prove that this is correct, so you can access that video from the cards right now and also from the descriptions part. So using that formula, we know then that if Q is equal to CV, then V is equal to Q over C. So I will write that, minus Q over C. And what is this Q? This is the Q at any time. This is in fact what we are trying to find. This is Q of t. Just like I here, the current is I of t. They are both functions, but I don't explicitly write that because, well, it takes space. And what does this equal? Well, we're back at A, right? Because there is no circuit element here, so this is also A. So we're back at VA. And I realized we didn't even use B, right? Did we? We basically didn't need to define B, but we just did, okay? Anyways. So we can see that VA is going to simplify on both sides. And we have that epsilon minus IR minus QC equals 0. Okay? And here, the way to solve this is to realize that, or to know that, the current I is dq by dt. And this makes perfect sense because, I mean, the current is by definition how much charge moves at a given period of time. And if we are interested in the instantaneous current, let's say, we need to use a differential, we need to use a derivative. And as I was saying, this makes sense because if we multiply dt, we see that dq is this. And this is just telling us we have some current, and as time passes, charge is going to build up on the plate. So we're just going to write this then. We're going to substitute that. Epsilon minus r dq by dt minus q over c equals 0. Here I'm going to, tidy up the equation a bit. Let's use that terminology. So after the tidying up, we get this. And I will make a substitution here. You don't need to do this, but to make it nice and clean, to keep it neat, I want to define A. And this is just, it is just a variable. It is going to be epsilon minus q over c. And it is not a constant because q is changing. It is basically the left side here. If I take the differential on both sides, it is dA equaling epsilon is a constant. And then on the right we have minus dq by c. So dq then is negative c times dA. Cool. If I were to substitute this here, then on the right, on the left, we have A. On the right, we have R. Then for dq, we are going to write negative c dA. So negative c dA divided by dt. Now, I want to have dA and A on the same side so that I can take an integral. And for that, well, let's just do this, right? Let's just do this. If you do this, yes, they're on the same side, but how can we integrate this? How do we take this integral? Okay, we can't do that. So we need to put it, we need to divide by A, not dA, okay? So if we do that, we're going to have then, and also I am going to multiply by dt and divide by negative rc. If this step is quick for you, please pause it and try it on your own, but you're going to get negative dt over rc equaling dA by A. Okay? Now we are ready to take the integral on both sides. On the left, it starts from time 0 to up to time t anytime. On the right, it's going to go from a naught, some initial a, to at, the a value at any time. On the left, the integral is going to give negative t over rc. We plug in the upper boundary, it is still negative t over rc. When we plug in the lower boundary, we get 0. So we just write negative t over rc. Equaling. What is the integral of dA by A? It is ln, absolute value of A. And the ln is there to assure that the argument of the natural logarithm, the absolute value is there to assure that the argument of the natural logarithm is positive. Because if it is not, it is out of domain for the function. We have the boundaries at, a naught, and this is going to be ln at over a naught, okay? Now, I am not interested in a actually, because we just made it up. Let's just substitute for it. Ln of epsilon minus q over c, and remember, this q is the function q, the thing that we're looking for. It is changing with time. Divided by epsilon minus q naught over c. This is the initial charge. The Q naught is the initial charge. And we can get rid of the absolute value, in fact, because the bottom side is positive. How do I know that? Well, Q naught over C is the initial voltage across the capacitor, and it is less than the voltage of the battery because there is also the voltage of the resistor. Alright, so we have an voltage of the battery, some amount of it drops in the resistor and through the resistor, and another amount, the remaining amount, drops across the capacitor. So the capacitor voltage is less than the battery's voltage. And the same idea applies to the top as well. The current is not going to be So what I was saying, yes, it is going to be the same thing because at some point the voltage across the capacitor will be the same as the voltage across the battery, and at that point the current will be zero. So the capacitor voltage will not change anymore, and at that point epsilon is equal to the voltage across the capacitor. So the voltage across the capacitor, which is this, if it is equal to epsilon, then it's going to give you zero. It's not going to give a negative number. Okay, maybe I complicated the explanation, but I hope it is clear to you that this division is positive, so we don't even need the absolute value, okay? And if it is not clear, please write it in the comment section. I will do my best to explain it further. Now, if we take both sides to the power of e, like so, we're going to have then e to the power of negative TRC. We got rid of the ln, that's why we took it to the power of e. We have this, okay? And I want to multiply the top and the bottom of the ratio by c. I'm talking about the right side, so it is going to be epsilon c minus q divided by epsilon c minus q naught. And if we solve for q of t then, which is in fact the q here, what is it? Well, let's put the negative here, then we can change it. It's going to be, let's see if I can manage it. Hold on. Let's have it though, okay. It is going to be epsilon c minus q naught. We have this factor. Then we're going to subtract. Okay, cool, then it's going to be this. I get rid of this negative sign. Q of t, it is going to be, I believe, like this. Let me be sure. I'm doing it again in my head. Yes, that is correct, I think. This is the formula. And the good thing to do is to check the constraints. At time equaling 0, this gives 1. So we have epsilon c minus q naught. These minuses, so these will simplify, and minus gives you a plus. So we have q naught initially, which is correct. And if t goes to infinity, we expect to see epsilon c, as we discussed. The voltage across the capacitor should be epsilon, so the charge on the capacitor should be epsilon c. And if time is going to infinity, this goes to 0, because this goes to 0, and we in fact have epsilon c as the charge on the capacitor. So this was the charging formula. You can also try to do the discharging formula for this setup. And the discharging formula, the derivation differs only by the idea that I is not equal to dq by dt. It is equal to negative dq by dt, because it is in fact decreasing the charge on the capacitor. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. So for that, please make sure to subscribe. And this is it. Thank you for watching. Hope to see you in another video. Until then, take care.